Today, let's see about saddle points of real valued function of several variables. Real valued functions of several variables. Let's see the definition first. A real valued function of several variables denoted as f of x1, x2, etc. xn is a function that takes n input variables x1, x2, etc. xn and produces a single real valued output. The domain of the function is the set of all possible n tuples of real numbers and the range is the set of all real numbers. Now let's see what is a critical point or a stationary point. Critical points or stationary points of a function are the points in the domain of the function where either the first derivative of the function is equal to 0 or the derivative does not exist. If x is equal to c is a critical point for a function f, then either f dash of c is equal to 0 or f dash of c does not exist. Let's consider an example. In the function f of x is equal to x square, the derivative f dash of x is equal to 2x. Therefore, the stationary point occurs at x is equal to 0 with a value of 0. Next, let's see about saddle point. Saddle points in a multivariable function are those critical points where the function attains neither a local maximum value nor a local minimum value. Saddle points mostly occur in multivariable functions. Let's see an example. This is the curve for the function x cube. The plot of y is equal to x cube with a saddle point at x is equal to 0. Here, at x is equal to 0, the slope of the tangent is parallel to the x-axis. So, its derivative at x is equal to 0 becomes 0, and at x is equal to 0, the curve attains neither local maximum nor local minimum. So, x is equal to 0 is a saddle point for the function y is equal to x cube. Let's see the method of finding saddle points. Let f of x, y be a function of two variables whose first and second order partial derivatives exist and are continuous on a domain containing the point a, b. Using the following steps, apply the second derivative test to find the extreme points and saddle points. Determine the critical points a, b such that the partial derivatives fx of a, b is equal to fy of a, b is equal to 0. Discard those points for which any of the partial derivatives does not exist. Next, calculate the discriminant d is equal to fxx of a, b into fyy of a, b minus fxy of a, b square for each critical point. Next, we check for the following cases. First one, if d is greater than 0 and fxx of a, b is greater than 0, then f has a local minimum at the point a, b. Next case, if d is greater than 0 and fxx of a, b is less than 0, then f has a local maximum at a, b. If d is less than 0, then f has a saddle point at a, b. If d is equal to 0, then the test fails. Let's see an example. Find the critical points of the function f of x comma y is equal to y square minus x square and check for the presence of any saddle point. Let's see the solution. Let us find the first order partial derivative with respect to x and y to determine the critical points. Here fx of x comma y is equal to minus 2x and fy of x comma y is equal to 2y, which exists everywhere. At the point 0, 0, fx of x comma y and fy of x comma y becomes 0. Then clearly f has a critical point at 0, 0. Now let us apply the second order partial derivative test. Now fxx of x comma y is equal to minus 2, fyy of x comma y is equal to 2 and fxy of x comma y is equal to 0. Therefore, the discriminant d is equal to fxx of 0, 0 into fyy of 0, 0 minus fxy of 0, 0 square is equal to minus 4 minus 0 square, that is equal to minus 4, which is a value less than 0. Hence, at the point 0, 0, f has a saddle point. Thank you.